Welcome to Chemistry Online. Today we're going to talk about heterogeneous equilibria. If you have an equilibrium that occurs across a phase boundary, this is referred to as a heterogeneous equilibrium. We've talked before about water being in equilibrium with vapor. This is where we get the vapor pressure due to water. If we have a closed container, the pressure due to the water vapor is going to be a constant. It doesn't matter how much water you have, the vapor pressure is a constant at a given temperature. The reason for this can be thought of simply as the difference in the concentrations. Water itself is 55 molar. At 25 degrees, the vapor pressure is about 0.016 moles of gas per liter. That is so much less than the concentration of water itself that we can just treat water as a constant. Therefore, we can say the equilibrium constant here is simply equal to the partial pressure of water at that temperature. Likewise, if we had something like this, calcium carbonate in equilibrium with calcium oxide and CO2. Calcium carbonate and calcium oxide are solids. The CO2 leaches out slowly. Neither of these solids undergo a significant change in concentration, so we say the constant is simply due to the partial pressure of CO2. We can take this and talk a little bit more about our law of mass action. We've said before that the equilibrium expression may contain partial pressures or molar concentrations. Solids and liquids will never appear in an equilibrium expression, and as we said before, we can write an equilibrium constant based on a balanced equation, stoichiometric coefficients. Again, this is partial pressures, stoichiometric coefficient, products over reactants. Let's look at a couple quick examples. Solid sulfur plus oxygen give sulfur dioxide at equilibrium. Again, we're going to ignore the solid sulfur. Our equilibrium constant is simply products over reactants. Let's return to the autoionization of water. We said earlier that hydronium and hydroxide are both present at 10 to the minus 7 molar at 25 degrees. If we were to write an expression for this equilibrium, we would not include water because it's a liquid. Only these species that are dissolved in liquid. Therefore, Kw, the equilibrium constant for this, is simply hydronium times hydroxide. This is the value that we wrote as 10 to the minus 14, and again we refer to this as Kw, where W stands for the autoionization of water.